Hello everybody, welcome back to my channel. Today I wanted to do something a little different. I have this good old friend of mine who likes puzzles and every now and then he sends me some. And he sent me this uh, padlock code puzzle and gave me the idea that this might be an interesting thing to do using an optimization model. So I figured why not make a video of this so that I can illustrate as an exercise how to use integer programming and binary variables to solve a fun puzzle. If you are not familiar with binary variables and logical conditions, I recommend that you watch my video on that topic. And I'm going to leave a link to that in the description of this video and also here on top for you to click. So make sure you watch that first so you're familiar with those concepts. So let me begin by explaining what the puzzle is about. There's a padlock and it requires a 3-digit code. And we're going to assume the digits are distinct. And then you're given a few hints about what this combination could be, right? So for example, it's saying out of the 682 combination, if you were to try this one, it turns out that one of these three numbers is correct and it's in the right place. If you were to try this other combination, turns out that one of these three numbers is correct, but it's in the wrong place, and so on. A few more hints here. So the goal is, can I use these hints to find out what the combination to open the padlock is? And of course, you could just sit down with pencil and paper and work through these and you would find the answer. But the purpose of this video here is to show you how you could use what you know about integer programming and binary variables to also model this as an optimization problem and find the answer. And then imagine if you had a larger version of this with, let's say, more digits. It might take you a very long time to do all of this by hand. So using the computer like this might save you time. And in the process, it's a great exercise for you to practice those concepts. So let's begin. So we have three places where to put the digits between 0 and 9, right? So I created here a box of binary variables, and the idea is the following. For every digit between 0 and 9, I'm going to decide, am I going to place that digit in position 1 or 2 or 3 of the padlock combination, or maybe in none of those, right? Maybe I won't use this digit. And that's the idea of these variables. So for example, this variable here is a binary variable that says, are you placing digit 3 in the third position? Yes or no, right? Or are you placing digit 6 in the second position? Yes or no? And using these variables, we can implement this puzzle as an optimization model and then use solver to find the answer. So let's think about this. First of all, it's true that in every position I need a digit. I can't leave it empty, right? So if I were to sum these binary variables here under a given position, out of those 10 yes-no variables, exactly one of them has to be yes, right? Because that is to say, exactly one of these 10 digits has to be placed in position 1. And likewise, the same is true for positions 2 and 3. Exactly one digit has to be in position 2, and exactly one digit has to be in position 3. So these three constraints will take care of that. We have the horizontal counterpart of this constraint, which is the following. Well, if I were to sum these cells in this row here, what is the meaning of that sum? Well, these are saying, did you place 0 in position 1, or in position 2, or in position 3? Well, first of all, because the digits have to be distinct, I cannot have more than one yes here, right? Because that would mean I placed 0 in more than one position. So I'm going to say at the most, one of these three yes-no decisions can be yes. It is also possible that they will all be no's, meaning I did not use the digit 0. That's okay, right? And the same is true for every digit. So I could take this formula or this constraint here and simply replicate it, right? For every digit, it's going to be used at most once, right? So this is true here. Okay? Now, if you wanted, because we know that the numbers in this column E are either going to be a 0 or a 1, basically what column E represents is, was the digit used? Yes or no, right? If it turns out to be a 0, I didn't use the digit. If it's a 1, I used it. And I'm going to use column E, these cells here in column E, in a minute. You'll see why. Great. So we have inputted first the constraints that are implicit to the problem, right? They were not explicitly given. They're just part of what I need to happen. Place one digit in each position and use each digit at most once. Now let's go to the hints and see how we can implement them as constraints. So let me begin with the 682 hint. 682 hint says the following. First of all, out of these three numbers, 682, one is correct, exactly one. So I can interpret that in terms of a constraint in the following way. I'm going to use exactly one of these three. So if I look at, did I use number 6? And I add that to, did I use number 8? And I add that to, did I use number 2? Out of these three yes, no's, exactly one has to be yes, right? So exactly one of these three things has to happen. This is the one correct number. And the other thing is, and whichever number is correct, it is in the right place. So the other statement I can make here is, if I look at the following three yes-no decisions, did you put 6 in position 1? Or did you put 8 in position 2? Or did you put 2 in position 3? Out of these three yes-no decisions, exactly one is yes, is correct, right? So I can say similarly this. And these two constraints here basically do what this hint 682 hint is giving me. They take care of that. Let's go to the next hint, the 614 hint. 614 says, again, there's one of these numbers is correct, like before, but it's in the wrong place. So let's take care of the one correct. It's similar to the one we just did. I'm going to use exactly 1 among the numbers 6, 1, and 4. Right? If I look at these three numbers, did I use those numbers, 6, 1, and 4? I'm going to say I'm going to use exactly one of them. Exactly one of those is going to be yes, I did use it. And secondly, the number that I use is in the wrong place. So basically what this means is putting 6 in position 1 is wrong, putting 1 in position 2 is wrong, and putting 4 in position 3 is also wrong. Right? So I can implement that in the following way. When I look at the decisions 6 in position 1 and 1 in position 2 and 4 in position 3, these should all be no's, right? Don't do it. So I'm going to say equals 0. None of those three things can be a yes, can be equal to 1. None of them. Great. Let's look at the next hint, the 206 hint. This says 2 of these numbers are correct. Well, it's a variation of the previous one. If I look at, did you use the number 2? Did you use the number 0? And did you use the number 6? Out of those three yes-no decisions, exactly 2 should be yes. And finally, even though 2 of these are correct numbers, they are both in the wrong place. So what I'm going to do next is to say, well, placing number 2 in position 1 and placing 0 in position 2 and placing 6 in position 3, these are all wrong, right? Meaning all of these 3 yes-no decisions should all be no. Should be no 3 times, which means 0 plus 0 plus 0. That means it equals 0. Now let's look at the 780 hint. 780 hint. And this says the following. Out of these 3 numbers, 1 is correct. Well, we know how to do that. 7, 8, 0. Exactly 1 is correct. And unfortunately, it's in the wrong place. So that is to say, putting 7 in position 1, putting 8 in position 2, and putting 0 in position 3, all of these are wrong. So no plus no plus no, or 0 plus 0 plus 0 is 0. And finally, the hint 738. So here, it says the following. Nothing is right. Basically, none of these numbers should be used. They're all incorrect. And of course, as a consequence, they're in the wrong position. So the easiest way to implement this is basically say, I don't want to use the 7, I don't want to use the 3, and I don't want to use the 8. So I could do that by simply going to column G here, right? Because it says how many times can you use a number? Well, 7, I don't want to use it. The 8, I don't want to use it. And the 3, I don't want to use it. Okay, so I'm implementing this hint in column G. So I'm gonna say C column G. That's where I implemented the directions of that hint. And this pretty much takes care of all the hints we were given and the constraints in the problem. So let's put this into solver to find the answer. First of all, what should be the objective function? Well, this problem actually is what we call a feasibility problem. The only thing that we are looking for is for an answer that satisfies all the constraints. There's really no minimize or maximize anything. But because solver needs an objective formula, we can simply pick any of the formulas we typed and make that the objective. Let's say this one. It doesn't really matter. And also the max min doesn't really matter. Leave any choice there is fine. My variables are my yes-no decisions in yellow, right? So this block here from B3 through D12. And the constraints are the following. First of all, let's say that our decisions are binary, right? So the same block of yellow cells, we choose binary for them. And then we're going to say use each digit at the most the amount of times you are allowed to use them. For some of them is don't use them, and for some of them it's use at the most once. The other thing is for every position you have to pick a digit. So the row 13 there should be equal to what's in row 15. And then the last thing is to enforce these hint constraints here, right? So the formulas in cell B17 through B24 should equal what's in D17 through D24. And that should pretty much cover it. Because everything is linear, we switch to the linear programming solver. Just to double check, because we have integer variables here, in this case the binary ones, I don't want this ignore box to be checked. And let me make this optimality gap percentage 0. It wouldn't really matter in this case, but as we've been doing this for all of the examples, let's just keep doing that. And click OK, and let's solve this and see what happens. Let's see, it should solve pretty quickly. And it found a solution, so let's take a look. Where did it place my yeses? So there's here, and here, and here. So what is it saying? Put the 0 in position 1, put a 4 in position 2, and a 2 in position 3. So the code that will open this lock is 042. All right? And if you double check all the hints, you'll see that we have satisfied them all and everything. So this is pretty much it for this example. I thought it was an interesting change from the typical examples that you see in courses like this. It still exemplifies the power of using binary variables to make yes-no decisions. It illustrates some other examples of logical conditions that you can use. And it's fun because you're solving a cool puzzle. And imagine again, as I mentioned earlier, if you had more digits, it would be quite time-consuming to solve by hand, especially if you had a lot of hints. So you can pack these into a model that solves it for you. And one last comment I wanted to make. Depending on the collection of hints, it's not necessarily the case that there is a unique answer, right? If you invent one of your own puzzles and you want to find out, well, is this the only answer? Is there another answer for it? One way you can do this is the following. Well, once you solve it the first time, if you want to find out if there is another answer that fulfills all the hints, you could simply force the solution to be different. That is to say, pick one of the ones in this yellow box and force it to a 0. So for example, let's say I want to know if there's another solution that isn't 042. In this particular puzzle, I already know there isn't another solution, but let's say I didn't know that, or if we were modeling a different one, what you can do is this. I want to find out if you can find an answer that doesn't put the 0 in position 1. So I click on that cell, B3, and I say flip this from a 1 to a 0. And I add this to the solver, and I can solve again. Once I solve again, if there is an alternative answer, you will see it. It will populate the yellow area. If there isn't, the solver will say, I couldn't find a solution. In which case, you can move on to the next position and try to zero out the one binary variable in that position and see if you find another answer. So you can see here, solver could not find a feasible solution. That means there isn't another valid code that doesn't put 0 in position 1. Well, it could still be that I can have a 0 there, but another digit in position 2. So to check that, you would keep going and say, I'm going to replace this formula here. I'm going to change it to be now C7. That is to say, what about changing the digit in position 2, solve again, and keep going like this, and this would allow you to find an alternative solution. All right? Okay, so that's what I wanted to tell you about this particular example. I think it's a fun exercise to work on. Maybe you can try to invent your own puzzle, maybe with more digits, other hints. So I hope you guys enjoyed this video and had fun with it, and I'll see you back here for the next one. Bye-bye.